Hey everybody, it's Jonathan Haggerty, and today I'm going to show you how to find the yield moment, the plastic moment, and then the plastic section modulus as well as the elastic section modulus for an L-shaped angle. So, as you can see here, I drew out a little diagram. I chose an L3x3 by 1/2 randomly. And we're using A36 still, that common still, so our Fy is going to be 36 KSI. Now, as you can see here, I went to the back of the appendix, and I pulled some of these values here that you can see. However, I'm going to solve this as if it was a built-up section, just so you can see how it's done. So step 1 is finding the E and A, the elastic neutral axis, or the y-bar. And as you can see, we took the total A dy over the total area, and we get that the y-bar is 0.93 inches from the bottom. And if you look back over here at the table, you'll see that they have 0.929, so we're basically right on the money. So then we need to find our I as our second step. And you can see this big long equation we have the Ix equals the total of the coefficient of the base times height cubed over 12 plus A dy squared. And when you solve all of this out, you're going to end up getting 2.22 inches to the fourth. And again, if you check in this J column here for the L angle, they get about 2.2, so we're a little off, but not too much. Alright, so here's where we find our first section modulus. So this one is for the elastic, and it's labeled S. And we take this I that we just found, and we divide it by the C. Now what is the C? Well, the C is just the total height, which 3 inches, and we're going to subtract off the y-bar from it. So 3 inches minus 0.93 gives you 2.07. And so when you solve it out, you get that the S is equal to about 1.07 inches cubed. And the textbook gives 1.06 inches cubed, so we're right on track. So My, our yielding moment, that's just equal to our yielding force times the section modulus, so 36 KSI times 1.07 inches cubed. And we get 38.58 kip inches. Now we could convert this to kip feet, but I decided since it was such a small member and such a small number already that we would just leave it in kip inches. So now the hard part, finding the plastic section modulus. So we start out by acknowledging that A1 equals A2, which is about 1.375 inches squared when you divide it evenly. So our first step is we want to find our P and A, H. So we take that area total over 2, which equals that 1.375 inches squared. And we divide by the width, which is going to be, for this purpose, 3 inches. And we get 0.46 inches from the bottom. So it'll make it, if our elastic neutral axis is right here, we've got our P and A about right here. And again, if you look at the YP here for the book, we get about 0.46. So we're actually right on the money with that one. So then we're going to have to find our different area concentrations. So we know that A1 equals the A total over 2 divided by the width. So if you look back here, A1 is this little section right here. And so we're going to take the total area of that, which is the 1.375 inches squared, and we divide it by 2 to get the 0.6875. And we're going to use that 3 inches of width, and that gets us our 0.23 inches from the bottom. So again, that'll be, if you were to draw a line out, about halfway between the P and A and this bottom dimension right here. And so now we get to A2. So A2 is a little bit more tricky because it involves taking the whole entire other piece here. But we also have just a tiny sliver of leftovers from this bottom rectangle. So the equation there is 1.25 inches squared over 2, which is the area of the top rectangle over 2. We're dividing it by its width of 1/2. So then for the second part that we're adding on to it, I said, okay, 1.375 minus 1.25, and that gave us 0.125 inches squared. I'm dividing that by 2, and then I'm going to divide that by the 3-inch width this time. And you add that together and you get about 1.27 inches from the bottom. So that'll be about right here if you were to draw the line. And so now we can find the Z, which is our plastic section modulus, by doing the total summation of the area times the A. And so we do 1.375 inches squared times 0.23 inches, and we add 1.375 inches squared times 1.27 inches. And we get that Z is about 2.06 inches cubed. Now, if you look in the table here, you'll see that they have that's 1.91 inches cubed. And so that's about 0.15 or so inches cubed off. It's not a significant difference, but do keep in mind because of the different flanges that could be there, as well as the fact that most angles aren't flat, they're angled a little bit. That's probably why we're getting a little bit of difference there, but this still seems okay to me. So we find the shape factor next, and we just take the Z divided by the S, so 2.06 inches cubed divided by 1.07 inches cubed. We get a shape factor of about 1.92. And then finally, we're going to find our plastic moment. And so that, of course, equals the yielding force times the Z, or 36 KSI times 2.06 inches cubed. And that gives us 74.25 kip inches. And here's my final diagram here. If you have any questions, leave a comment. And thank you so much for watching my video. Have a good day. Bye-bye.